So what I want to do here is that we talked about the photoelectric effect. And one of the things that I said was that it's the easiest way to see that classical physics failed. It really is the easiest way to see. And the reason why it's so easy to see here is because dim light shined on a metal can eject electrons. And it just shouldn't happen at all. If you look at the wave model for light, it should not happen at all. So the way we had the setup here is that we have two metal plates that has the battery connected. And right now there's nothing on this metal plate, but I can change the battery to make it negative. I have a light source coming in, it ejects electrons. A lot of times people call them photoelectrons. And it goes this. So what you're finding here is that when we think of, light shining on metal, I mean, to be honest here, what you found here is that people didn't believe in atoms when this experiment was done. So when I make the statement, light strikes the metal, energy is absorbed by the atoms get excited, and then they eject an electron from the atom. Well, they didn't think about them in terms of atoms. So note that when I make that statement, it's a very different statement than what they were thinking. But we're more advanced because we got to stand on the shoulders of giants in order to get to where we're at now. So what you find here is that there's a lot of problems with this thing. If you believe in the wave model of light, there's a lot of problems. And I'll tell you that the wave model of light is extremely, extremely successful. It predicts almost everything of what we observe. The only reason why there's a problem was because you are now able to shoot light at a material where you couldn't ignore the atom. Beforehand, you could ignore the atom. But the invention of Maxwell's equations and the techniques that came with them allowed you, by the way, Maxwell didn't even know atoms existed. He heard about them, but he didn't. His theory, Maxwell's equations, don't have anything about atoms at all. Any interpretation of atoms is way after Maxwell, and mostly because of Heaviside. So to think what, going like, how could they not think that? I'm going like, no. I mean, it was Albert Einstein in 1905 that really gave the best proof of atoms. And so what I'm saying here, even though I call them strange features right here, they're really major problems for classical physics. One of them that I said here is that the light intensity increases, you would also expect the speed of the electrons to increase. Yeah, you could imagine if there's blinding light outside and you're getting burnt more by the sun, you probably think that the light has more energy coming at you. And you would think that compared to, less intense light, that it has less energy. Well, it turns out that that's not what was observed. And the way you measure the speed of electrons, as we talked about, that we change the battery to be negative, and as these electrons are moving towards this plate, they start to get reflected. And as they start to get reflected, what we find here is that it's like the electron going up an electrical ramp. The height of this thing, remember, is called the voltage, which is an electrical height parameter. And when it runs out, that's essentially when the electrons are turned back right at the end here. So we find here that the intensity of the light does nothing to change the maximal kinetic energy. That is a strange feature. Something is wrong right there. And then the next thing that we said here is that the speed of electron does increase with frequency. So that means that the color of light matters, which is kind of surprising because typically if we think about light, we think about the intensity of the light. If the intensity of the light's really high, you got to be putting more energy into it. What the hell does the color have to do with it? But that's not what the photoelectric observed. The photoelectric, ooh, I had a sneeze. So it turns out that frequency, okay, thank God, now that's out of me, hopefully. So if I have a higher frequency light like violet versus lower frequency light like blue, higher frequency light like violet produces higher kinetic energy photoelectrons, whereas blue produces lower kinetic energy. So if I'm looking at this picture-wise, this is what I'm seeing here. And then we went into the applet and we showed that violet light actually had the electrons going further. I mean, they go higher up the incline. These guys go less up the incline. So if I was to sort of like draw a picture of this thing, this is kind of what I mean by this thing here. Let me increase this in size a little bit. Looks like it's a little bit small. Let me see if I over. So if I had an incline, right? Here's my incline. And you could imagine that if I have a blue, if I have a blue photoelectron, let's say that it's, you know what, let me be careful. It starts off down here, but it only gets to this height right here. So that's the maximum height that it does. But if I start off with the violet electron, because the light has more energy, the violet goes up higher up the incline. So if it goes higher up the incline, this means that it must have a larger initial kinetic energy. Because this guy goes lower, it has a smaller initial kinetic energy. And that argument only comes from this argument of conservation of energy. And that's what you're seeing here. This goes further to the right, higher up the incline. This goes less far, lower down the incline. And another strange feature that we said here is that there's no delay in time of ejecting electrons. But that's really out there. And the reason why that's out there is that light waves, even if they're wavelengths of the order of nanometers, atoms are tiny, much smaller than that. And then they got to transfer the energy from the atom to the electron. And so the energy, concentration on such a small area tells you that that should be really, 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 really hard. So because atoms and electrons are extremely tiny, the time to absorb electromagnetic wave energy takes time. But that's not observed. So that's another one. So there's three things right there that there's a problem with the wave model of light. But that's not what we're here for. Okay? What we're here for is this one right here. And I would say this fourth piece, so the wave model cannot answer the three, but the nail in the coffin is this right here. And I say, here is the strangest of them all, right? The strangest is this. So what you find here is that as frequency is decreased, right? As frequency is decreased, there comes a point when electrons stop being ejected. Regardless of the blinding, how do you spell blinding? I think it's like this. Blinding intensity of light, right? So if I decrease the frequency, there comes a point where the electrons stop being ejected regardless of how bright the light is. However, when shining, dim light, electrons are ejected, right? They're ejected if the frequency is high enough. Now, you're probably thinking there's no way that, okay, so dim light can eject it, but blinding light can't. So to try to get that point, I have a crazy analogy. I think it's a good analogy, and I think it's right. So here's my analogy now. Okay, so when I think about my analogy here, what I imagine here, this is what I call boats in the bay. Okay, so you could imagine that I have some boats in the bay. I mean, how do you draw boats? No idea, but we could just, right? And then of course they're in water, so you gotta do water. And then, you know, some of these boats are pretty, so we gotta color them in. And then you could imagine that we have several boats, because it's important to talk about several boats here. Okay, so here's my boats. And what's special about these boats here is that they're tethered. They're tethered off the coast here. And so that means that I got what? Well, I got this. Of course, there's all the water here, right? And what these guys are doing here is that they're going to set anchor down. Right? It's important that they're anchored in. Now, they're anchored in there pretty strongly here. So you have a fleet of boats. Let's not write it here. Let's write it here. So you have a fleet of boats firmly anchored. In the bay. So here's what's important. What do I mean by firmly anchored in the bay? What that means here is that big waves cannot pull out the anchor. Now, this is super important in the sense of the analogy is concerned. And the reason why it's super important here is because what this is really talking about is that this represents that blinding light can't eject electrons from the metal. So the anchored boats tell you that and that big waves can't take them out, do that. So now you could imagine here that this thing kind of goes up like this. And again, here's the water. And then we got a grassy knoll or something, or a beach, whatever you want to think about this. And so now, to your surprise now, incoming ripples, right? Tiny little waves, little ripples, right? Incoming ripples, suddenly, makes a single boat it shudders, rises high out of water, and is thrown onto, So in other words, like if I start to focus on this guy right here, all of a sudden, what ends up happening? Here goes the boat. Little ripples are doing what? Right? They focus on one boat, and that boat, with its dripping water as it's being thrown, is suddenly thrown onto the shore here. This analogy, this is dim light ejecting an electron out of a metal plate. So just think about this. You have boats that you have incoming waves that are anchored that are not able to knock out any of these boats out. But yet you get these ripples that are floating in the whole bay. And yet one of these ripples can take a boat out and toss it out of the water and throw it onto the shore. You got to admit, that's crazy. There's no way that should happen here. So if you start to think about this thing, this is what I consider the simplest case, right? And the question begs here, how could these mere ripples do this? How could these mere ripples throw out a boat like that? Maybe if you capture all the energy of all the ripples in the bay and then concentrated them into one spot, maybe you could see that there might be enough energy to take one out. But the energies of these ripples are spread out throughout the whole bay. So that's nonsense. It seems, and another thing that seems really strange, it focused only on one boat. What about these other boats? Right? How can you toss one of them and leave the neighbors untouched? That's another really crazy thing. But the bottom line here is this. This should not happen, which tells us that it's a big failure of the wave model of light. There is no way that light as a wave could answer this question. And so that now ends that discussion. And so what we're going to do now is that next here, we have to go in and we're going to start talking about Einstein's proposal here. So let's go look at that. So to solve this is a dilemma right here. Okay, right? This is a big deal, right? Let me write this nice and big. It's a failure of classical physics. And what we're going to do now is that the resolution brings in Planck's constant, h. Before this, there was no resolution. Now there is a resolution. So let's go look at this thing here. Now we look at who enters the picture? Einstein's proposal. So what do we know? This is what we know. We know that Planck claimed it was the atomic oscillators that were quantized. Right? It was the atomic oscillators that were quantized energies. But when light, but I said ooh, but wait a minute, I shouldn't have said when, but that light remained a wave in the radiation field. What do I mean by that? So picture-wise, I imagine the following thing. I imagine the oven again. So when I'm thinking about the oven, remember what I mean by the field here. What I mean by the radiation field is I mean what? That I have these smooth waves inside of this thing. So what that means here is that in the walls here, I have what? I have oscillators. So as oscillators are vibrating, they emit and they absorb energy in quantized states here. And as they emit waves in quantized states, that means I can form standing waves inside the oven. So that's what I mean, that they remained a wave in the radiation field. So you set up electromagnetic waves in the oven here. But what did Einstein say? Einstein came back and he said the following thing here. He says, that's not what happens. So when you look at his picture here, he says that this radiation is not made up of waves, that when I have little oscillators going up and down in the walls of the oven, what he says here, Einstein claimed this was not true. And what he said here is that the radiation field is itself quantized, right? And when he says this quantized thing, what he's saying here is that he defines photons as the energy carriers of light. Okay, he defines that they have this universal characteristics. So that means as these oscillators are doing them, you're sending out little things like this, little quanta of energy packets, and they carry the energy. And I cannot tell you, right? So these guys right in here are the energy carriers. That are quantized. And let me tell you, that causes some serious grief. Think about that. That light is not a wave. That light is this energy packet. And you might be thinking, oh, no problem. Well, I mean, how many times have you said to yourself, well, light has this wavelength or light has this frequency? Guess what? That doesn't exist. And the photon model, so as soon as you do that, you're discarding hundreds of years of the belief. Oh, hell. I forgot how to spell belief, something like this. The belief that light was a wave. And let me tell you, I'm pretty confident that you're probably the same way. Do you ever talk about the wavelength of light? You ever talk about the frequency of light? Photons do not have frequency or wavelength. And that's got to be disturbing because we've been told that our whole lives. So then Einstein then says that he says that photons have universal characteristics. The first thing he says here is he says that the energy packets are quantized. And what do I mean by that? It says that if I look at the total energy of light, it's actually equal to the number of photons times their individual photon energy, where the photon energy is now given by what? Planck's relationship. So this right away is clashing with Planck, because Planck says it's the oscillators. Einstein says, nope, it's the light itself that's quantized. Then he says that light is a stream of compact energy packets. Sometimes I call them lumps, sometimes I call them packets. And effectively, what this implies here is that they kind of act like bullets per se. So we should be very, very careful. What I mean by bullets is that it's localized, right? This implies that it's localized energy. And then the last thing here that I want to say that's universal, and you got to be really careful here because the language in textbooks is very poor. Okay. By the way, even Einstein said it initially this way, but it's been shown that this is not correct anymore. A single photon is absorbed by a single electron. Let me say this loud and clear. A single photon is absorbed by a single electron. Not true. They are absorbed by the atom. Light is absorbed by the atom. Okay? And it gives all of its energy to the atom. Okay? It gives it to the atom. But what does this mean? This in turn excites the weakly bound electron which can be excited. Which can be ejected. From the atom. And I should also say that the photon ceases to exist at this point because it's got completely absorbed by the atom. So those are the things that Einstein says. Photons have universal characteristics. Energy packets have the energy given by Planck. They come as streams of little bundles. And a single photon gets absorbed by the atom And that in turn can excite and eject an electron. So let's talk about metals. And what you're going to find here is that when we're talking about metals, metals have the property that some of their electrons are loosely bound. That's what makes it a good conductor here, right? So I should probably say that metals have weakly bound electrons. And inner electrons with extremely high binding energy. So one model that we can talk about for bound electrons is an electric potential well. But before I get there, I'm going to do an example first. The first example that I want to look at is I want to ask the question, what does a copper atom look like? Okay, what do I mean when I say, what does a copper atom look like? Oh, damn. You know, I got to go get some images. I got to get out of this page. I didn't think about this. Shoot. Okay. I have my images right in here. Then I want to go get one more thing. So let's look at this copper atom right here. So what this is that I just pirated from some online website that has a periodic table here. And what you're looking at here is that, note that there are a couple of numbers that we should look at. Let me see if I can make this a little bit bigger without making it too big. And what you're seeing here is that if I look at copper, what this tells me here is that copper has 4 energy levels. So this tells me that it has 4 energy levels. I know that you might say, no, they're orbitals or shells. Actually, orbitals and shells are different than energy levels. Energy levels are more complete. Orbitals and shells, the way they use them in chemistry, unless they're talking quantum mechanics, are not the same. They're close, but they're not the same. And what this tells me right here is that tells me the number of protons, but also the number of electrons. So when I think about an atom, this is kind of the thing that I think about. Well, what I find here is that I have a nucleus, and this nucleus is positively charged. So copper has 4 energy levels. So I'm going to go 1, 2, 3, 4. Did it look this way? No, but that's okay. We're among friends, so it doesn't matter. And what you're going to find here is that these electrons are then spread out to, so if you look at the table here, what you're seeing here is that there's the first row has 2, the first shell, or the first has 2, then if you count, there's 8, and if you go to the next one, there's 18. And when you get to the very last one, note that there's that number 1. That guy here is the 29th electron. So what you're seeing here is that there's 2 kinds of electrons. I mean, they're not different electrons, but if you look at the first 3 shells, I call these the inner electrons here. Okay. So now let's go look at this thing a little bit better now. So what we want to do here is that one of the things that we see here is that these inner electrons are tightly bound. And if you try to get some of these out, you got to use some serious energy. In fact, to get some of these inner electrons out, you need to use X-rays. You got to shine X-rays onto these things to do that. So they're tightly bound, and they stay put. So the only thing that could be ejected is the 29th electron, which is a weakly bound electron. So now let's draw a picture of this thing here. So if you look at the picture of this thing, the way we draw things in physics is that we draw potential function diagrams. So what you're going to find here is that I'm going to come in and I'm going to draw a potential diagram. And what you're finding here is that they actually look somewhat like a bowl. It's more complicated than this, but they really do look pretty close to this. So what you're seeing here is that they actually have a bowl-shaped type thing here. And then this here is the maximum energy. And so you could imagine that right in here is this potential energy function. And what you're finding here is that there's a couple of things here. So this guy here is the potential function. Okay. This guy over here is the radial distance. And this guy right here, that line right there, this is the minimum energy. Required to remove an electron. Okay, so if you can get to that energy level, you can eject an electron out of this thing here. Now, what you're finding here is that we got to go back and look at the atoms. Look at the atoms. Look at those red atoms. Excuse me, I said red atoms. Look at the green electrons or the red electrons. Where are the red electrons in here? So these are the electrons. They're at the bottom of this thing here. And what we say here is that here at the bottom, so right here, what you're seeing here is at the bottom of the well, is the trapped inner electrons. That will not get out. And that's what these guys over here do here. So the question is, where are the weakly bound electrons? So up here at the top here, I could have other electrons there, but I'm only going to show one. What you're seeing here is that the 29th electron here is close to the surface of the metal. So it's right below the surface of this potential function here. And so, by the way, this guy here, this represents the edge of the atom. So what people do here is that That's a lot to draw. So what do? They simplify the picture. And when they simplify the picture, they create a model for this scenario here. So when you're looking at this model here, what they do here is that they focus at the very, very, very top. And when they focus at the very top, what they do here is they come in, they go, okay, let's look at the very top of the electrons that can get out. So then I come in and I go, oh, this is what it's looking like now. And what you're seeing here is that down here is still that red layer that I'm showing you. And what you find here is that now, if I'm talking about a copper metal, then there are numerous weakly bound electrons at the surface here. And so what you're seeing here is that this guy represents the depth of the well. Okay, it's the depth of this well here. So what you're seeing here now is that what is the photoelectric effect now? So the photoelectric effect essentially says this, okay, I'm going to send in some packet of energy. What is this? Well, this is the photon that comes in. And what does the photon do? It gets absorbed by the atom, and as it absorbs by the atom, one of these electrons is going to get excited. So as it gets excited, I can then eject one of these electrons out, right? Right? And so then in this scenario here, this is the ejected electron here. But the question is, we're still dealing with the metal now. So let's go deal with the metal. And one of the things that we say here is we say this. I want to focus on the depth now. So if I look at this guy right here, what you're seeing here is that the depth is the electric potential. But what do I call the electric potential function? It's the binding energy. But what's the binding energy? It turns out, did you find the following thing here? Is that they define this as the work function. And this work function is defined by the capital Phi here, which tells us how much work is required to eject an electron. So when I look at this thing here, picture-wise, this is a quantum mechanical picture, but I think it's really a good one here. It goes like this. Well, if I have a little well versus a deeper well. So when I'm looking at these wells here, what you're finding here is that the electron is essentially down here at the bottom. So as that is at the bottom, we ask the question, which requires more work to eject it? Well, because this is a little bitty one, I write a potential function like this here. This guy, because it's deeper, has a bigger potential function, and so therefore it's going to tell you here that there's more energy required. So if I have a smaller Phi, then that means that I have a less deep well, which then tells me that it's easier to remove. Whereas if I have a larger potential function, then this is a more deep well, which then means that it's going to be harder to remove. So then what I need here is I need my values here, and I gotta take this guy, I gotta bring it down. So I'm gonna make this a little bit smaller. And so what you're seeing here is that here is how people can experimentally measure the work functions. So in this case, I should have had the symbol here. So when I look at them, you could see here is that look at sodium and look at platinum. What I want to do here is that I want to compare both of these. And what you're seeing here is that the work function of sodium, that is 2.28 EV, versus the work function of platinum, which then reads 6.35 EV. And you can see here, because sodium has a lower work function, it means it's going to eject. If I shine light on them, I'm going to eject them right. It's going to be easier to eject them. Whereas platinum requires more energy to eject them because it has a deeper well. So here's Einstein's question now. So Einstein asked the question, how much energy is required to eject electrons out of a potential well? And what he does here is he applies conservation of energy. And he does this thing right here. He says, okay, here's my well. And I know that this well has trapped electrons that are weakly bound. And then he says, I'm going to focus on one of these things here. So what you're seeing here is that you shine light and you have a localized bundle of energy, right? So this is a localized energy packet. And as it comes in, what you're seeing here is that the energy of this photon is the energy given by Planck. But remember, this is for the photons. Planck said it's for the oscillators. And then what you know here is that this represents the work function or the potential energy of this thing. And then afterwards, one of these electrons is isolated and it leaves with kinetic energy here. So then he comes in and he says, using energy conservation, what does he write here? Well, he says the following thing. He says, okay, I know that the photon has a certain amount of energy, right? This is its energy right here. And when I look at that energy, I know what it is because that's what his model predicts here. And then, since this is my zero value, the well is below the ground. So then the well has a certain amount of potential energy here, which is negative. And then afterwards, I can eject this thing to get a certain amount of kinetic energy for this electron right here. Okay, so again, even though I don't think I've said it yet, this is the metal surface, which means that its potential energy is zero, which is the same as the work function here. So then if V applies conservation of energy, it says that the energy of the photon minus the negative energy of the metal, that this will equal the kinetic energy. Now we got to be careful here. What you're going to find here is that this kinetic energy is going to turn out to be something like this here. It's going to be K max minus some constants. And I'm going to draw some pictures here in a moment here. But what we say here is that we ignore this term generally because this assumes no energy loss due to collisions. And I'll get more to this in a minute. What do I mean by that? So the photoelectric effect equation then reads that K max is then equal to HF minus the work function. And this is what he does here. He writes down that photoelectric effect equation here. So then what happens here is that he realizes that you can measure K max. So then Einstein says you can measure K max, which we already talked about it, using what? The photoelectric effect experiment, right? And what I mean by that is that I got to go get that image for the photoelectric effect here. And what we're seeing here is that we're seeing this type of thing here. So if I go get that image, I want to go get this guy right here. Oops. So what you're seeing with the photoelectric effect here is that one of the things that we said here is that we're going to shine light, right? As you shine light, it's going to come here, and what are you going to do? You're going to eject electrons. And these electrons now, some of them are going to be moving with a Kmax thing here. Now, the key thing here is that you got to remember that these guys are going to be what? These are my metal plates right here. Right? Here's my metal plates here. And when you're looking at these metal plates, let me remind you real briefly that what I mean by that is that I have this metal plate and I have this metal plate. And so when I'm looking at these metal plates here, this plate here is going to be made negatively charged by the battery. And so when I model this thing here, I'm modeling an inclined plane here. So if I now look into the potential picture, I now have electrons that are going to do what? They're at the bottom of the ramp, and I shoot them with some kinetic energy. In other words, with that amount of kinetic energy, right? That's what we mean. And so when the electrons get all the way up to the top here, they get turned around, but they have V max at the very end. So that means they got to get all the way up to the top up here. And that means they have converted all of their energy into what? Potential energy. They convert all their energy into electrical potential energy. And this electrical potential energy is related to E versus stop here. Now, one of the things that I want to remind you here is that this voltage is the electrical height required by the incline to stop electrons. Okay, so what I mean by that is that, think about it this way. If I look at that incline, if I have an incline like this versus an incline like this, this guy here has a very small V-stop. This guy here has a much bigger V-stop. So what this means here is that if I have a smaller height, what do I mean by height? Electrical height. I'm going to have a smaller V-stop.
V voltage, not to be confused with velocity.
No, not to be confused with velocity.
Because it's actually like reciprocal of velocity.
Yeah, you know what? In fact, I'm going to get rid of that V over here and call it maximum kinetic energy. No V's, but V stop. And then that means here that this has a lower K max. But if I have a higher V stop, so if I have a larger,
you have maximum kinetic energy indicated at the top of the ramp.
Yeah. Here, I'll show you what I mean in a minute here. And then if I'll have a larger V stop, so therefore I'm going to have a higher kinetic energy. So this is what I mean by that. So imagine that I have this red electron. How much kinetic energy do I need to get to the top of this ramp up here? Well, according to this, I need that amount of kinetic energy. So I don't need that much kinetic energy to get up to there because I have a lower stopping voltage or lower height. But if I have a violet one and it comes all the way up to the top here, then that means that this height here is going to require a bigger kinetic energy max to get up to the very top. And that's exactly, by the way, this picture of the incline is the exact model for parallel plates. There's no deviation here. This is not an analogy. This is actually a mathematical calculation. So what we do with this here is that we rewrite the photoelectric effect. And what you find here is that we know that we have K max, and then this is going to be E V stop minus, equals HF minus the work function, which then tells us that now this is what Einstein really wrote. He wrote this guy right here. And this is essentially the equation that got him the Nobel Prize. Because you can measure the frequency of light, you can measure the work function, so now you can predict the V stop that goes along here. So when you plot these things, look at what happens here. And these plots are very, very powerful. So let's plot this. What you're seeing here is that I have, they plot V stop, and then they have frequency that they're looking at. And what they have here is that, let's say that I have a metal that looks like this. And so the intercept right here of this equation is going to be minus phi divided by E. And what you're seeing here is that there's a region right here. So what you're seeing here is that, so if I look to the left of the cutoff point, and I haven't described what the cutoff point is yet, but I'm going to say that this guy right here is the cutoff point. Okay, so now look at this thing here. So if you're over here in this region, there are no electrons ejected. And you can see that the dashed line tells you if it's going below the axis, how can you have, remember that V stop is proportional to K max. How can you have a negative kinetic energy value? You can't. So then this region over here, this is where electrons are ejected. So you need a minimum frequency in order to eject electrons. If you're not there, you won't see any electrons. And remember, that is a big deal. So the cutoff frequency here then, right? So left of the cutoff frequencies, no frequencies, how do I say this? No, that's not what I want to say. Okay, I know what I want to say. For frequencies below the cutoff frequency, which we typically define as frequency cutoff, no electrons will be ejected. No matter how intense the light is. And that solves a lot of those problems right there. So it's a big deal. So let's say that this is sodium. So earlier we said that sodium had a really low value, but I could have a different metal. And what you'll find here is that I could have a metal that goes like this. And I think this one, I think we called platinum last time. So platinum is a different metal. And what you're seeing here is that here's its cutoff. So what you're seeing here is that different metals have different cutoff frequencies, meaning that it's harder to eject things out of platinum than it is out of sodium. So if I look at this thing here, so the work function of platinum, as we saw earlier, was greater than that of sodium. So that means when I look at V stop, so K max, which is E times V stop, at the cutoff frequency, that must be 0. So then that means here that this is going to be HF cutoff minus the work function. So you could see here is that the frequency of the cutoff is then going to be phi divided by H. So you could see that it's directly proportional to its work function or its binding energy. So before we get into the examples, I got to tell you about 3 important relationships. Should you memorize them? I think you should. One of them you don't use as much, but you should at least know 2 of these by heart here. Here are 3 important relationships. Okay, you're going to use these for the rest of the semester. This one's one of the big ones. Just memorize that thing. I mean, don't even, you use it so much, it's like ridiculous. The other one here, which is, this one's a little bit more complicated to remember. So any frequency calculation will require this. And the other one is the one that you've all learned from 4C or 4A. It's the wave relationship. You want to remember these guys. Okay. What I need to do here is I need to go do an example. And I have my examples on that sheet, so I got to go back up here. So if I go to my examples here, I want to look at this guy right here. So let's look at this thing here. There's a lot to unpack on this question because there's some things that I haven't told you yet. It says, light of wavelength 200 nanometers shines on an aluminum surface. 4.20 electron volts is required to eject the electron. In other words, that's its work function. Now, what we want to do now is that from this, what we're going to do is that it says, what is the kinetic energy of the fastest and the slowest ejected electrons? What is the stopping potential for the situation? And what is the cutoff frequency for aluminum? or the cutoff wavelength. So the first thing that we should do here is that we should do a series of pictures. Okay, so let's draw pictures of this thing. Picture-wise, what does this mean here? Well, I want to draw 3 different potential wells. Okay. Actually, I want to make these a little bit further apart. At least this one. And since they're all the potential wells, this red here tells me that this is the depth of the well. Right? They all have that. Now, what you find here is that if I focus on just one electron, let's say that I'm focusing on this electron right here, what we find here is that if I shoot in a photon, the photon gets absorbed by the atom, which excites the electron, and we know that this is the height. This is the binding energy. This is the electrical potential energy of the electron in this well. So you could imagine the following thing here, is that if I take an electron and I barely eject it out of the atom, right? I'm barely ejecting it to this point right here. And what you're doing here is that you get K max, the kinetic energy of this thing is 0. Okay, so what you're finding here is this here, is the following thing. What you're finding here is that this is the slowest possible slash electron out of metal. Now, one of the things here is this, that this electron will get reabsorbed into the metal. And the reason why that is here is that if you take an electron off of a copper ion, it makes it more positive. And if it makes it more positive, it just sucks it right back in. You have to have some initial kinetic energy. So then, what do I mean by K max? What do I mean by K max? What you're finding here in these metals is that you have a collection of electrons that are weakly bound. So that means I have electrons that look like this in that upper layer. One of these electrons is going to be right at the top. And then you see these other electrons that are going to be at the bottom. And so you could imagine that if I have these scenarios now, where I'm now going to focus on these 2 green electrons right here. So now if I shoot a photon, at these things, I could then take one of these and I can eject it out where there's no collisions, or I could take this guy here, and if this guy absorbs it, I could probably have a series of collisions. So what you'll find here is that this kinetic energy is not equal to the maximum kinetic energy.